Okay, connecting. Is this gonna work? I think we're live. Welcome to the Common Body launch. I don't know if we can see comments on here, but can someone check if the YouTube's actually live? You all have phones? Oh no, it's upside down. Is that okay? That is not okay.
Yep.
We're live.
Yep.
Okay, I should have thought about this before I made it this way. It had to be this way.
Is it vertical or horizontal?
No.
Yeah, you're right.
Hang on. Let me think quickly of how to... That's upside down. Could we get a Allen key to flip this to the other side? So we can't turn the stream around. We're gonna turn, cameraman has his phone mounted on that side. So we're gonna mount cameraman's phone on this side so you guys can see the body launch filmed by a comma body. Mike and Billy are over here in the audience. Hi Mike. Hi Billy. Yeah, we're flipping it around.
Just like the weight. Buzz over here is not happy with
Oh, Buzz? Oh yeah, cameraman's a little wobbly. All right, have you ever been on a boat before? It's like that. Let's clean on the bathroom and go over to the spot. What do we got in the comments from YouTube?
Mike turned around.
We'll see you on YouTube. Thanks, guys. Join us on
I tested it with the weight on the other side.
Doesn't have an online weight.
There we go. Oh, yes. No, cameraman, no. Stay. Okay, you're being filmed by a comma body. This is experimental technology. You'll learn... Whoa. Okay. Chill. Ashwagandha. Alright.
The mask seems to be the correct amount of weight. Oh yeah.
Oh. Is George just leaving here?
More. Yeah. I prefer that.
Look. People are going to complain about how sick they are from watching this video. It's
Stabilization. The future is full of discomfort.
the future's full of discomfort. Did you bring your shirt for your body?
I have a flight jacket, but that was too heavy.
Oh.
So this is something pretty.
Oh, Buzz lost his flight jacket?
Yeah.
All right, how much is YouTube complaining about the rocking?
I,
Not much.
I'm getting sick.
Being on a boat.
Come on.
Good classroom presentation.
Cameraman, you know, normal people would lose their job for this.
Oh, someone asked what the body's pronouns are.
It. It's. Look at how stable vehicle researcher is. Look, cameraman, you can learn. It's because he's wearing a mask.
Let's see. Can we control it at all? It's on you, great.
All right, you have a good framing of the shot.
Yeah, we do actually.
All right, cameraman.
I think you
not
should close
bad.
the door though.
What time is it? What are we gonna do for 12 minutes?
I don't know.
Oh, we gotta add everyone in Discord. I'll go do
Yeah,
that.
and we should post it on Twitter.
Post it on Twitter. Okay, you know what? Do we have some blocks?
No, I asked for this today. I want to jack up my body for development.
Yeah. Can we put them on some? Can we put them on some blocks? Like we got. It's rocking back and forth pretty bad.
Ah, that's fake.
No, we got like a cinder block or something.
No, it won't fit.
What do you mean?
I mean, you have the legs, and then you have the.
Yeah, but I'll put a cinder block vertically. The body's balanced very stably when they're not holding weight, like vehicle researcher. My phone's heavy though. Maybe we can. Oh! I got it stable, but I can't rotate it now.
If you change your mind, I think this is the perfect size.
Oh, wait, is this a RTX 3090 box? Perfect for playing Minecraft in 10,000 FPS. Oh, let's zoom out here. Okay, so I had to download some app to do the YouTube because the real YouTube app didn't work. All right, it's stable now. We just got to frame the shot. All right, wait, I'll go ahead everyone on Discord.
Where's the future of human rights robots? Did you name a body?
Do we have a mirror so everybody can see cameraman? Is Buzz causing trouble?
Yeah, he's definitely gonna start a fight at some point.
Let's bring, hey Mike, what are you doing up there? Come here, Billy. Cameraman's very stable.
Yeah, but he's doing it the wrong way.
Well, yeah, but that's a later problem. Who's in charge of YouTube comments? What are you doing?
Turn 'em.
You're gonna turn them. Okay, very carefully. No, don't turn the phone. You have to turn the robot. If you turn the phone, it will go unstable again. Okay. Come here, cameraman. I know. A normal person will be fired from your job, but you don't get paid much, so we keep you around. Okay. No, stay. You had one job to do, and it was stand still. Oh. Okay. Up, 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 up. Okay. Oh, look, he's stable now. We put him on some blocks. Okay, cool. Check out how the shot's framed.
Looks pretty good.
See if it's good. Is Mike coming over here?
I'm just gonna leave it here.
All right. I'm sorry if you flew a long distance to come here for this. All right. Is the shot good?
Yeah, the shot's great.
From YouTube? What's YouTube saying?
They want to know where the other bodies are. I agree. You should get some bodies.
Oh,
somewhere.
yeah. Come here, Mike. Come here, Mike. Let's go. You wanna, Joseph, you wanna connect to Mike and, oh, you got something to do. Who wants to connect to Mike and drive around? I tried connecting to Billy this morning.
I'll connect to Buzz.
Did I miss something?
I know the
Oh, no, you didn't miss anything.
Why not
You're just getting here, missed nothing. Can I see the screen well?
Cameraman who's trained on 40,000 hours of GoPro skydiving. Do people there ever actually work?
At Comma? Yeah, we worked mad hard. How do you think all the bodies got built?
This is a different one, right? You can control mine. Apparently, I should control the robot.
Oh, yeah, chance, man. I already destroyed one.
Alright.
Oh, you already destroyed one.
Yeah. Oh, I got this. Shane probably takes
Cameraman has Parkinson's.
Drive the
Alright,
mic.
guys. Do you want to get a few more in the picture? What about vehicle researcher? We get them all, and I think it's worth it to get them all.
Can't be reached.
Vehicle researcher, don't you?
Oh,
Alright, George.
Ready? It's early, so. It's almost
6
10
minutes?
o'clock.
6 minutes?
Six
We're gonna give you
minutes.
6 minutes of entertainment.
So what should we talk about for 6 minutes? Oh,
Just signal.
who's driving?
Shane. I wasn't allowed to drive.
Oh, Shane.
I forgot which one
You
is
gonna
that.
get him over here? Shane's bringing
Don't
bus.
knock into camera.
He looks great.
Vehicle researcher is very stable.
I'll turn him around then.
So all the
So you-
code,
you gotta
doing the
put it in
balancing is running in
That
Python.
was really difficult. Here you go.
Buzz looks amazing. He's looking at some neck issues.
Oh, careful.
Don't knock into cameraman, whatever you do. Cameraman is the only employed body here. It's great.
Vehicle researcher is a very
Alright,
important
guys.
job.
Oh. Reverend wants to know where the new office is.
Oh, it's nearby. Yeah, we're moving into a new office, so we'll actually have space.
20,000 square feet.
Yeah.
This is fine.
This is so funny.
And hopefully, you guys saw on the way in. See our new data center. Racks and racks of computers. Those are half full. Those are full. Oh, you mean over here? Yeah. Well, so we got 2 more of these R730 racks coming in, and then we got another data center in the garage, which is the one here. It's all going to get re-racked into these guys. Buzz, do not knock into cameraman. You're very close.
All right, we got 4-minute countdown.
All right.
We have 288 people. I think we just started a little
We
early.
got 288 people in the YouTube?
Yeah.
Okay. If everyone's here, I think we can start. Is the shot framed well? Are these bodies too much in the way?
No, they're great. I really think it'd be nice if Buzz got it.
Okay.
I gotta get Buzz back in there.
Whoa, do not knock into camera. All right.
Buzz is a little
All right,
bit more
buddy.
aggressive than
So this is probably one of the most recorded events because the bodies are all cameras. They're all watching. Okay. So, what you see here are coma bodies, and they may not look like much right now, but they are the future of people. I want to remind everybody that once people didn't look like the future of people, if you think about it, if you look at the Earth 40,000 years ago, you saw the ferocity of lions, the magnitude of elephants, the speed of cheetahs, and you wondered how the little squishy things would come to inherit the Earth. But here we are 40,000 years later, and nobody questions humanity's complete and utter dominance over the animals. When's the last time you've seen a bear on the way to the coffee shop? So the Silicon people are coming, and you know, it's not going to take 40,000 years. It's probably going to take maybe about 40, and in 40 years, nobody will question the dominance of the Silicon. And the reason humanity came to dominate the Earth is our brains. And the silicon brains are about to go way past human brains. One of these is maybe about, maybe equivalent to a human, if you really wrote good software. And then if you got a machine with 8 of these and a rack with 40 of these, well. Okay, so yeah. Now, of course, you know, you could talk about all the highbrow, singularity, philosophical stuff, but let's focus on the very concrete. Bodies are very concrete. One of the slogans we have at Comet AI is that Comet AI is real. A self-driving car is not a car. This is a weird thing that's like been put into people's head by images of Google pod cars and stuff. Here's a Rolls Royce and a guy. And the self-driving car is, again, not the car, it's the guy, right? Be self-driving. You see most of the letters in self-driving car are actually the guy and not the car. So we need to stop. I mean, like, you can look at these things, special purpose robots. This is a vacuum and this is a mop. The vacuum and the mop have exactly the same brain. They're doing exactly the same thing, just one of them has a vacuum attachment and one of them has a mop attachment. Then, you know, you have to buy the same thing again when you go buy your robotic lawnmower. It's basically the exact same thing. It drives a path, uses slam, all that, and then, you know, you can go even further with the special purpose robots, and then like this is, well, why did anyone build this, right? Again, a self-driving car is not a car, just as these robots are not lawnmowers, mops, and vacuums. The thing that you want is one robot that is vaguely human, plus, well, you know, a vacuum. You can buy on Amazon. Mop that you can buy on Amazon, a lawnmower you can buy on Amazon, and a car you can buy on Amazon. So yeah, you want to not do the special stuff. You want to just have one humanish robot with all these things. So when you look at the Comet 3, you can see Comet 3 is atop the 5 bodies here. But Comet 3 is a head. It has 2 eyes, 2 ears. They're not active yet, but it does. Every Comet 3 has 2 ears. It has a mouth. Maybe you've heard it talk. It beeps right now, but it's capable of, you know, producing. It has a very good vocal tract. It's capable of producing all human sounds. It has a nose. Maybe you've seen it breathe. When it gets hot, it breathes. It breathes out. It has a brain. Snapdragon 845. Maybe on par with a bee brain. Not quite a human brain yet, but you can see these things maybe have the intelligence of bees. And then it has a spinal cord. You can look at the spinal cord running. You see Mike's spinal cord right here? So this has a spinal cord that connects to your car as well. 4 CAN buses, power. So I guess the blood vessels built into the spinal cord as well from the brain. In order to drive all the cars, people think, oh, what are you going to do about Toyota security? How are you ever going to support my 1968 Ford Pinto? Well, stop thinking about it in terms of a special purpose machine that connects to a car and talks over some fancy electrical interface, and start thinking about it as a machine that gets into the driver's seat and presses the pedals of the steering wheel. That's the real API for cars. And this API has been standardized for 100 years. So how do we build something that interfaces with that API? And the cool thing is it also interfaces with the API of the broom, and the API of the mop, and the API of the lawnmower, the API of pots and pans in your stove, and all of these things. So what you really want to build is, it doesn't have to be humanoid, but it has to be humanish. So in order to drive all the cars, clean your house, cook your food, etc., the Comet 3 needs a body. And this is the Comet body. Here's the Comet 3, here's the body, and here's the human for scale. This is what it looks like on top. This is what it looks like on the bottom. And you can buy it right now at cometbody.com for for $999. So go out there and buy them. We have a little betting pool going on in the office about how many bodies we're going to sell. This is what the footage looks like from the body. This is from the office. You can connect your body remotely. This is from our Europe office. So these things are fancy 360-degree cameras. We've already shipped about 20 bodies out for Body Epot. Here's a user YouTube video.
Hey.
Well, the body needs some space to get up to speed. And, we'll talk about a generic way to address that in a little bit. So yeah, we've already shipped out the Body Epot problem program. You know, Epot stands for Experimental Prototype Hardware of Tomorrow. We shipped out some Comma 3s in the Epot program as well. Watch that again. On and off. This is what the bodies look like clothed. This is what the bodies look like naked. It's very compact. Ships to you, only domestic, not international. But it folds up nicely and fits in a box. It comes to you with nice assembly instructions on the internet. This is what the internals look like. So this is a hoverboard motherboard with a custom board on top of it. We also replaced the microcontroller on the hoverboard motherboard with a STM 413. The exact same microcontroller that's in Comma 2, Comma 3, White Panda, the Gray Panda, Black Panda. So it runs Panda software, and it's talking directly to the MOSFETs, which just means there's zero lag on these motor controllers. Right? You have full control. The software is all open source. That directly drives the motors. Maybe you want to bring a wheel out? Yeah, bring a wheel out. You know, when you think about what these wheels on these things are and why this stuff kind of wasn't possible maybe 10 or 20 years ago. Right? You go back to maybe, I remember in high school, 2005, trying to buy a brushless motor. And you could buy brushless motors. They were hundreds of dollars, relatively low power, and required these very specialized motor controllers. In the last 15 years, MOSFETs have become like 10x more efficient. You can get MOSFETs that are the size of my pinky that can switch a kilowatt of power. So Igor's going to bring a wheel out, and I'll just show you how far these things have come. They're hoverboard wheels, but they're sensored brushless motors, meaning they have 3 phases for the windings, but then they also have Hall effect sensors, so you can get instant starting torque, and this is all connected to the 413 microcontroller. We have current sensors on 2 of the phases, and then a general current sensor on the whole thing. This is what's on the hoverboard motherboard. Great. Yeah, these are what these things look like. When you just look at this, and that this kind of motor would have been so expensive 15 years ago. Neodymium magnets, brushless, and you can get the controllers for cheap also. Okay, look. We have to start something. We thought about buying one of those mesh suits, dressing somebody up, having them come out here and dance. But that stuff's ridiculous. That stuff's science fiction. This isn't the common way of doing things. Common AI is real. This is not. So how do you start? Right? What is kind of the minimum set of stuff required to start interacting with the human world in an intelligent way? And the answer is, first, let's start about with a way to move around. Right? Yeah, you can build legs, but why are you spending time on that? That's not where the hard problem is. Robotics is 99% a software problem. if you had magical, ideal software on the body, again, like I like to think of software written by God. If you had software written by God on the body, this thing could already do so many different jobs, right? It could do all kinds of QA and inspection, it could do security. Unfortunately, software is really, really hard. So right now, what does the body do? Well, the body balances. But it has the same logging stuff as what's in OpenPilot. So we're going to start gathering data from the bodies, and we're going to start training models that are capable of the first task that we want to focus on is localization, is being able to localize well in the environment. We have more than enough cameras and IMUs in order to do this. And then thinking about the,
We're gonna move the camera closer.
move the camera closer.
Yes.
Okay.
See.
Thinking about the general purpose robotics problem the same way we think about the self-driving car problem, which is don't hand code it. What does it mean to build, well, AI systems that don't, that interact with the real world, but don't have very specific, like, oh, we're going to detect a mop, and we're going to use an A-star algorithm to plan how our hand will wrap around that. Like, you can't do this. You have to, think about, well, what does end-to-end for the body look like? And this is not an easy problem, and I don't have an answer to it. I feel like maybe about 3 years ago, we had the full solution for self-driving cars. I still think we do. It's complete, we just have to fix all the bugs. And fixing, fixing all the bugs is really, really, really hard. But at least from a conceptual perspective, we have self-driving cars solved. And the question is, what's the next thing conceptually? So self-driving cars are a lot easier than, say, cooking. Because when you drive a car, all good drivers are good in almost the identical way. They'll take almost the same actions given the scene. For cooking, this isn't true. You can take a huge variety of actions to make an omelet. Think about it. Does it really matter if you put the pan on the left burner or the right burner? Does it matter if you crack the eggs outside the pan or inside the pan? So I'm getting shells. Right? It's a much more the loss function is much less maybe convex than the loss function for driving, where all of the does it matter if you're in the left lane or the right lane? No, but that's a problem that we can talk about very explicitly, and you can't really talk explicitly about the equivalent problem for cooking. Robotics is 99% a software problem. OpenPilot is the best robotics platform in the world. And I'll justify this statement. You can look at ROS. A lot of people in the robotics world are using ROS. ROS has a custom serialization format. ROS has a antiquated socket interface. ROS 2 was moving to ZMQ. We've already moved past ZMQ. So ZMQ is this, maybe some of you are familiar with the library. We've written our own thing called message queue, and the big advantage to message queue is you don't have to make a copy. So you can pass, it's a like publish subscribe interface where you don't have to send the packets through the kernel. You can just allocate some shared memory that's shared between the processes. And this isn't academic stuff. I'm sure many of you here today, many of you watching at home, have OpenPilot on your cars. This stuff is tested for over 1 million hours. It works at scale. It's just much more developed than any of the stuff I've seen from robotics. Maybe cars are one of the only examples of working robots in people's lives today. Like, you can look at a Roomba, but it's a joke. I got rid of my Roomba after it destroyed my second MacBook charger. So how do we take all of the good stuff in OpenPilot and apply it to more generic problems? With the magic of software, anything is possible. We don't just want to watch the world. And now the bodies just sit there and watch the world. Body add-on kits. The knee is coming in late 2022. So we started thinking about arms, but one of the problems with arms is if we put an arm up here, well, how useful is that, right? You got to be able to pick up the vacuum. So you need a knee. You need to be able to bend down. The knee also includes a hip. Arms are coming in 2023. And the price point that we're targeting for all this stuff is on the order of thousands of dollars. So when you look, all robotics in the past has fallen into basically one of two categories. There's toys, generally which fall in the realm of hundreds of dollars. You have like Lego Mindstorms, you have you know, a lot of these sort of toy robot kits. I bought a little 6 Degree of Freedom arm on Amazon for like $200, but they're useless, right? Or you have things in the tens of thousands of dollars. You can think about like Baxter from the defunct Rethink Robotics, or you can think about Spot. Boston Dynamics is now shipping Spots for 75 grand, right? That's well outside the budget of most people, but something that's on the order of thousands of dollars, it's not a toy. It's legitimately well built. You can look at these things. You'll have an opportunity to look at these things much more close, like a solid aluminum base, 80/20, which is easy to attach things to. This is being filmed on a slightly unstable body right now. It's professional grade robotics for a price point that's 10x less than everybody else pretty much doing this at this sort of level. So we're going to build arms. We're going to build arms that are capable of lifting serious weight, that are capable of, you know, they don't have backlash, they have very precise encoders on them, they're not like hobby servo motors. Look, the other philosophy also is minimal actuators. I believe when Tesla launched their bot, they talked about 40 actuators. It's never going to ship. Right? Well, it's never going to ship for any reasonable price point. Over here, this is a body with a knee. And you can see that there's 2 actuators, one for the knee and one for the hip. This allows pitch control and height control of the camera. These are the gearboxes that we're going to be using. Again, it's the same wheel, unable to play video, error 5. Wow. I have something better than that. Using the same wheel. This wheel has 9 foot-pounds of torque, 10-to-1 gear ratio, 90 foot-pounds of torque. Look, if you don't believe us, can we bring Kenny out here? There's one body you haven't met yet. So you've met Cameraman, you've met Buzz, you've met Mike, you've met Vehicle Researcher, you've met Billy over here. How you doing, Billy? You're very stable. Here's a battery indicator. This is the recording indicators. You can disable recording with that. Enable recording with that. It shows up in Comic Connect. It's just like a normal thing. Oh, yes. This is Kenny. Kenny's a little bit taller than the other bodies. These are those gearboxes I was talking about. 10-to-1 cycloidal drives, 0 backlash. We're going to put a very precise magnetic encoder on them. And then, we're not doing this in some tiny microcontroller. This is a good height. Oh, I like this. I feel like, you know, me and Kenny were like similar heights. This isn't being done. This doesn't have some tiny microcontroller, which a lot of these sort of toy robotics do. It also doesn't have a fancy computer, which is going to break, which is going to cause problems. Like, you know, you look at the Boston Dynamics thing, it's like a Core i7, it's like a full computer. It loses all the beauty of the reliability of embedded systems. Why do you think phones took over from PCs? It wasn't just their size. So it's the Comma 3, which runs Ubuntu 2004. It's OpenPilot, and it's so easy for us to do things like use MPC. Use the same MPC we use for cars to control these actuators, to place, you know, Kenny in different positions. Part of the reason these things are unstable is there's not that much weight. The Comma 3 is not that heavy. There's not that much weight in the top part of the body. So balancing like that's actually pretty hard. But with these things, it's going to be completely stable because we know the exact position of these things. We can compute exactly where the center of gravity of the thing is. So yeah, Kenny's going to be able to sit down. Gearboxes are back drivable. It'll be able to lay down, stand up completely. from completely laying down, and this provides a really good platform when we attach the arms up here to be able to crouch down, pick things up. So yeah, Kenny's gonna be able to do squats. And this is shipping at the end of the year, and it's an add-on kit for your body. So if you buy a body today, we'll sell the knee add-on kit. You just replace the bar with this bar, attach it, it's all on a CAN bus. Again, something that separates the hobbyist robotics from the professional robotics. It's CAN bus. This thing is basically a car. It shows up to OpenPilot just like a car, has a fingerprint just like a car. So yeah. Sorry Kenny's not on. See on version of Kenny probably in a couple weeks. Come with us on this journey. Body support is already in master on OpenPilot. This is not a separate repo. It required very few changes to OpenPilot to make these things work. The localizer that's running on the bodies to keep it stable is the exact same localizer that runs on the car. It's even using the PoseNet that was only trained on vehicle data, and that's one of the reasons for the rocking back and forth. But as soon as we start getting data from the bodies out in the field, we're going to put that training data into the vehicle models as well. And I think that it's not just going to improve the body, but it's also going to improve driving. Because you have this problem in the data that we get. And the data that we get, if you're expecting a rotation to the right, you're also expecting the road to be curved right. The action taken by the car is correlated to the environment. It's extremely correlated to the point that even though this isn't actually true, or the inverse of this is whenever you try to train a simulator from driving data, what you end up with is a simulator that when you tell the car to steer right, the road curves right. That's how it works, right? Humans know this, right? The steering wheel controls the curve of the road. Obviously. And there's nothing in the data to really show that that's wrong, because there's no points in our data, except for some really, really extreme ones, which are more rare than data bugs, where the human sees a right turn and turns left and, like, say, smashes into the wall, right? You as a human have no problem visualizing this. Everyone imagine a light right banking curve on a highway and taking the wheel and going like this. You all have no trouble imagining what will happen. But you can't imagine this because you've ever been in a car that did this. You've never been in a car that did this. You've never been in a car that was on a lightly right bank turn on a highway and somebody turned the wheel left and smashed into a dividing wall. But you can imagine, no problem, because you have a generic model for how physics works, for how, what's the word? How, like, projective geometry works, how you expect the scene to change based on how you move through space. You got this because you didn't drive for the first 16 years of your life. For the first 16 years of your life, you were in environments that look a lot more like places the body would be in. And by jointly training the models on driving data and body data, we can teach the car the same things. We still have to hand code, so the big thing, the way that we made laneless work and the way that we're going to make end-to-end longitudinal work is by using a hand-coded simulator. But the simulator is not hand-coded in the sense that we code the behavior of other objects. The thing that we're coding are these rules of projective geometry. So hopefully, with the body, they can learn this. Things not to buy. So these are our competitors. This is a Segway Lumo. This is an Amazon Astro. And I'll tell you what's wrong with both of these things. They are small and deserve no respect. Would you respect something that was 2 feet tall? 2 feet tall is about the height of Kenny's knee. Do you respect this thing? No, but seriously, like, imagine you, like, broke into a building and this thing showed up. And these 90-foot-pound motors started moving. We're building robots people respect, not robots that, what do you do? What do you do when you see an Amazon Astra? Imagine you broke into a place and there was an Amazon Astra. What's your first instinct? Exactly! You're gonna kick it. You want to kick Kenny? You can try. Kenny might kick you back. You know, I think the biggest, when you search for a security robot, you get this company Nightscope Robotics. Nightscope Robotics is, again, one of these companies that's in this 10x overprice. They're charging 70 grand a year for their robot. We already have all the stuff for security, right? You've seen Comet Connect. We're going to roll out Sentry Mode to the cars. So why not also do the same thing for the robot? We have all this logging infrastructure, you know, security robots for like 5 grand that set it up, and this is going to deter people a whole lot more than you know, a camera that they might not even see. Sit down, Kenny. Come on. I just like here. This is for that's like to scale. So, buy your body today. CometBody.com. $9.99. Ships in 1 to 3 months. First in, first out. And that is the Comet Body. Who's got questions? Hey, Kenny, you want to share seats?
I'm curious about like.
Be nice with his shoulder.
Okay,
Yeah.
As someone who is not really familiar with machine learning and stuff, I'm wondering like how many people would theoretically need to buy this to provide enough footage to have an impact on a model or training or whatever?
Not that many. Probably something like 20 hours of footage would be plenty. Even if we're the only ones with them and we're using them around the office, it's probably still enough. Like a small amount of data that just completely breaks the correlation of when I see something that looks like this, this happens. To start to learn the actual physics of the world instead of just, also, you know, on a car you can't explore. So if you think about in reinforcement learning, you have this explore versus exploit, right? Maybe this was also referred to as a temperature parameter, where sometimes you take an action that isn't the optimal action for a scenario, just kind of to see what will happen, do it sometimes randomly. Well, you can't really do this on a car, but on the body you can. It's a much, as a development environment, it's a much lower stakes place to try out changes to OpenPilot. As OpenPilot gets better and better on the cars, it becomes harder and harder to just like mess with something. Whereas on the body, you know, it's still, developing on the body is fun. All the low-hanging fruit is still there. You want to make that guy not rock back and forth? Spend 20 minutes tweaking the PID loop and it'll probably fix it. You know, spend a little bit of time learning. Like he rocks back and forth because he has a hoodie on. Billy's wearing a nice lightweight T-shirt. Okay, learn the parameter for the weight of the thing. And go slow learner on there. Like you can do that. You can play with this, and it's fun. Unlike trying to do that in a car.
So does it balance right now based on machine learning?
So
Or it's just kind of code?
the localizer is based on machine learning. So it's the same localizer that's running in the car. It's using the gyro. It's a Kalman filter, but the PoseNet is all machine learning. The PoseNet is trained on vehicle data. So once we start adding a few body segments, that'll all just will just work. Doing controls with machine learning, like the state of the art. Maybe the state of the art is Boston Dynamics. None of Boston Dynamics controls has anything to do with machine learning. You can watch videos about how Boston Dynamics does controls. They use machine learning for vision and for some other stuff, but the basic control loops are this state space linear model transition thing. So yeah, I mean, classical controls are just, you don't want a lot of parameters in your control system because you don't want, it's not high dimensional space, right? Like vision's a very high dimensional space, so you can learn a lot easier than trying to learn something that's, well, it's, you know, your output is 4 dimensions and your input space is not that big either. Say the input space is the whole camera, it's not really the whole camera. Right? How many dimensions do you really want to reduce to first? So yeah, the classical stuff still does better than the machine learning stuff. But this will start to change. And then the other thing about what you can do on the body that you could never do on the car is you can do reinforcement learning on the body if you want to do on-policy reinforcement learning. Like, again, it's a low stakes space, so download your OpenAI Gym cart pole solver. You know, cart pole in OpenAI Gym, it looks like this, and run it on the body, and maybe it'll work. Go try it. Buy one.
So, I'm not that fluent with machine learning, but what I'm understanding is that if self-driving is like, what would a human do in this situation? And you got the answer because you got all the data from the camera and stuff. But in this situation, I don't really see the answer. So I guess you just said reinforcement learning, but I think like it's a very different dimension.
It's a lot harder, yeah. So the answer could be the same, right? So you can say the same thing, right? Like say I want Kenny here to learn to make omelets. Well, the human has a policy for making omelets, and Kenny should learn the same policy. Now you're right; it feels different from driving. The driving policy seems a lot easier to talk about, and I think it's due to the linearity. I didn't mean convexity before. Linearity of the space, right? Like when I mean the space is linear, I mean it's like, well, if you're driving here, if you're driving like 20 centimeters off, it's almost the same thing. If you're putting the egg 20 centimeters off, well, that's a very different thing, right? The loss function is so much less like, you know, whether you put the egg on the right side of the pan or the left side of the pan doesn't matter, but you put the egg just a little bit over the pan and now your stove's a mess and, you know, Kenny gets fired. So yeah, I mean, what is the loss function there? Well, what's your loss function? What's the human loss function?
Good way to put it.
So like with machine learning, it's like a valley of happiness then, where like it knows where it works well, but doesn't know the time 100% where everything always works. Basically, is what you're trying to say.
I don't know what you mean by that. I'm saying that like the loss functions right now that we use for driving, in our driving model, is basically I don't know if we use the Gaussian or the Laplacian, but it doesn't really matter. It's some shape that looks like this, right? It's some very convex shape. Whereas the loss landscape for things like cooking don't look like this. And that's the difference. Now, this loss function, by the way, isn't perfect for driving. We can express some amount of stuff like we have both a mean and a standard deviation. You can look at our models, but it's not perfect to express like, well, okay, but that's a cone. You really don't want to hit that, but you can go on either side of it. You can kind of, it's not just a mean and standard deviation. It's multimodal as well, so there's 5 modes. But yeah, you want a more complex loss function than this.
Like what I'm understanding, it's actually very different from Boston Dynamics because Boston Dynamics have like certain goals. You basic, like their AI inside, you still hard code everything. But here you're saying like you learn by itself, like you will learn certain policies.
Yeah, I mean, Boston Dynamics is largely remote controlled, right? Like the spot's largely remote controlled, but they're still using on top of the remote control a lot of sophisticated control stuff, so it looks good. So the bodies are remote controlled as well, but the remote control doesn't remotely control the torque on each wheel. They'll never be able to drive it, right? But think of a remote control for a drone. Right? Imagine a remote control for a drone that has 4 throttles. Good luck flying that drone, right? But you have all this dynamic stabilization stuff running on the drone, and they've gotten very, very good to the point that you can give it a high-level command of, you know, move your position here or rotate. So we kind of want to get to the same point with this stuff. So we have I've been driving down the latency of the streamer from this thing. It's about 200 milliseconds right now. To stream that back to a computer, the joystick control is instantaneous. Not instantaneous, but like sub 10 milliseconds. So I want to drive that down to 100. And then I want to write an app for a VR headset. Put the VR headset on, and you can drive it. And this is going to be, I think, a nice way to drive the arms as well. You'll be able to use the Oculus controllers. You know, where you place the Oculus controllers, where you place the arm. You know, you want a knee, like this. You want a pitch, like this. right? And we can put things like the goal pitch angle, the goal height, the goal center of gravity, or the goal speed into a solver. The center of gravity is acceleration, but we could put that into like a MPC solver, and it'll output actual low-level commands to the motor. We might even have, like the way we have it on the cars right now is we have MPC, which takes the model stuff and turns it into a plan, turns it into a trajectory. So the model outputs a plan. One of the things about a plan is a plan doesn't have to start at the center of the car. A plan can start over here. Of course, you can never actually do that. So the model predictive control turns this, here's the car, here's this, into this. And computes your kind of recovery trajectory. And then there's even lower level stuff, like we have a PID controller and the steering loops in there. Also the actual like control a car with torque. You want to command it to an angle, there's PID loop for that. MPC outputs the angle, PID.
Yeah, I was just very attracted by the ideal, like the end goal, and then I didn't know how it would go there, but you explained it quite good, like get the controls first.
Yeah, like it's unclear if these controls are necessarily bad, right? Like you might want your machine learning to not have to deal with the lowest level torques. Maybe you eventually do, but that's not where the low-hanging fruit is for this stuff. The thing that you really want to avoid doing, that we're never going to do, is like you never want a cone guy, right? Because what's a cone? Now, that's a really hard question. What does it mean to control something to an angle? Well, it's a very clear question. Now, you might not be able to do it, your noise model might not be perfect. PID, for example, can't deal with things like latency, but you know, you can still talk about it in very physics-based ways, where there's no physics definition of what a cone is. We got any questions from YouTube?
We do.
What do we got?
How do you go about collecting data about learning human cost functions for things like cooking?
Well, so we think about what the actual intermediary goals of the body are. This thing is not going to be making you an omelet anytime soon. Do not buy it with the expectation. I do not want to hear in support, oh, I didn't make an omelet. I put it by the stove and told it to make an omelet. How do you collect that data? Well, here's one idea we have. So like I said, I want to write a VR app. And you guys can do it. This is all open source. We'll do it all open source. That streams the sensorium of this thing back to the headset and lets you control the arms. So one way we can train it is, can you make an omelet in telepresence? Can you use the body, use the arms, using the full human brain, and are our controls good enough to kind of smooth over? This is still a really, really hard problem and a really valuable problem. Building a telepresence robot that's capable of making an omelet under human control allows us to outsource the job of your chef to Bangladesh, right? Like, think about it. If we could build just a good telepresence robot, we've enabled this labor arbitrage for a whole set of jobs where it never previously existed. Wow, that's like $1 trillion. Oh, that sounds boring.
Oh, hope you don't mind.
What?
I'm part of the common Discord. Some people had some questions. So you kind of compare this to the like enterprise robots as opposed to like the Luma or like the Amazon things. So I considerably it is steeply priced. You know, to some extent that is understandable. Are you going to be warranting like the hardware components? Because I think some people heard that once you guys put hardware components in it, why is it so expensive and it's kind of risky.
If you don't like the price, don't buy it. Like that's all I'll say.
Yeah. Another thing from the Discord, somebody asked, will it be able to go upstairs?
Well, look at it.
In the
Again, software is magic.
future? Two of these guys.
Could Kenny make it upstairs? Well, if you put enough weight here. How am I doing that?
The
Huh? What?
Oh.
Well, I'm not using my, think about it. How can I jump, right? So I have weight here, do this. So yes, Kenny can jump.
How will this impact OpenPilot? Is this two products now? Is this taking priority? Is it a separate department?
So it's the same problem, right? Is it really different from driving? All the things that are specific to driving are things that you probably shouldn't be putting that much time into anyway. There's I think who wrote it? Richard Sutton, the reinforcement learning guy, wrote like The Hard Lesson of AI.
Which
I-
Sutton?
What?
Sutton.
Sutton, yeah. Everyone should read this. Basically, the more time you spend thinking about how to hand code something, the more time you're wasting. Like, it's going to be replaced by machine learning. It's a question of when. So the body forces us to think about what things we're hand coding on the car. And, well, if they don't work for the body, we have to ask why. So what is our company goal? Our company goal is to solve self-driving cars, because if you can't solve self-driving cars, you definitely can't make an omelet. It's way harder. So is this going to, are we changing the company goals and we're giving up on OpenPilot? No. It's the same problem. I think that just like the model with both data, with both body data and driving data, we'll end up learning something that's better at both the body and driving. I think that OpenPilot will end up being better at driving because of the body, and we wouldn't have done it otherwise.
I'm just reading the questions. They want to know, does the body have to watch me cook to cook?
So, does it have to watch you cook? I mean, that's even harder, right? So, one of the really nice things about driving as a problem is the car is a digitized system already. The car that you drive is the same car that OpenPilot drives. If the body watches you cook, it's not then controlling you, it's controlling itself. So being able to like learn using mirror neurons the way humans do is really, really hard, and we haven't even started to consider how to do any of that yet. Is the body going to be able to watch you cook to learn to cook? Ask me again in 5 years. Don't expect any of that. If you're buying a body, expect something that stands up. Oh, by the way, the other thing about the knee, which you'll get right away when you get a knee, is right now the body has a top speed of 3 miles an hour, largely because it has to lean over too far. And accelerating is really hard when all you have is this. This is not how a human accelerates on a hoverboard. A human accelerates on a hoverboard by shifting their weight forward. And that's what Kenny did.
What would you say the current run time would be with the batteries?
Balancing is about 6 hours. Driving around the joystick is about 2. The batteries are really nice. They have like a built-in BMS. You can like stick more batteries on. If you buy more of the batteries and you hook 4 of them up, I think it would just work. Eventually maybe sell the Kama stomach, just fill it with batteries. But you do the math. You do the math on 2,000 calories and how many watt hours 2,000 calories is. I forget what it is exactly, but it's like within the realm of feasible. It's like within the realm of feasible that you can fit a day's worth of human power in batteries. And once we have the arm, we'll be able to plug its own charger. You want to make a charger dock? Well, you need a charger dock, right? Humans don't have this. They have a feeding tube. Put the food in your mouth, right? Like plug its own. Magic of software.
Is there a specific task we'll focus on first?
Balancing. If you're expecting the body to do things, it's not for you. If you're expecting a high-quality robotics development kit that's fun to develop with, the body might be for you. But a specific task, all of the tasks that are really, I'll use a good business word, synergistic with the driving problem, we'll focus on in the body, like Sentry Mode, for example. All right, like Sentry Mode's both useful in cars and useful on bodies. Imagine this thing stands there, sends you a text message if someone comes into your house. Right? Same thing with the car.
Should I try to make my own body?
You can.
What ability are you most looking forward to the body having?
I'm not like, if I was Elon, I'd promise you that it would like, you know, it's gonna vacuum your floors by the end of the year. But, you know, that's like, I'm not Elon, so.
Are you saying it's too far out to even like think about that?
It's not that it's too far out to think about. It's that I couldn't give you any timeline on it.
Sure.
It's hard enough to make timelines of when we're gonna ship 0814. We're really bad at timelines. Everyone is. Everyone is. Everyone's bad at timelines. The only question is how honest you are with yourself about this. Right? Some people are very dishonest and manage to continually do this. Right? It is amazing. Like people will say that they'll have something done in 2 days, and they don't have it done in 2 days. And they'll tell you in 2 days, by the way, that it's going to be 2 more days. And then they do not. And you're like, okay, can we like eventually you'd think that something about the human would correct this broken loop, but. The reason you don't is because like there's 2 ways to estimate timelines. One way to estimate timelines is to think about each task. You're like, okay, well if I want to make something that vacuums, okay, well first we're gonna have to be able to pick up a vacuum. Okay, well maybe that's like a 2-month project. Okay, and then we're gonna have to be able to like move around. It's maybe a little harder. Maybe that's like a 3-month project, so we'll be able to vacuum in 5 months. This is an absolutely terrible way to think about this. A much better way to think about it is how long have projects like this taken in the past. And it's taken us maybe 5 years to learn to drive cars as well as we have, so 5 years to learn to vacuum. Like again, yeah. Maybe if it's a similar order of magnitude problem, which maybe it's way harder.
Have you guys tried like small projects internally and see how like maybe like avoiding a table like?
But this isn't a good way to think about it, right? This is the same problem as like, oh, well, oh my God, the people who want like, well, can you just add an adjustment to OpenPilot so we can adjust the position in the lane? Like, no, this is a huge waste of time, right? And it's the same thing with the thing that avoids the table, right? Like, yeah, sure, you can waste, you know what? You can write a prototype of that in a week, right? I'll download the latest YOLO V7 and put it, it's something else now, and put a table detector and I'll use a depth net and it'll avoid tables 80% of the time. I'll make a really good video that doesn't show the broken 20% and it'll look impressive, right? But it's a stupid waste of time, right? So no, this is the wrong way to think about it. People think about driving like this too. People are like, well, let's start with an easy task. But you do this and if you're not focusing on the problem holistically, you're not getting anywhere towards solving it. There's a saying about self-driving cars, that self-driving cars are demo complete, meaning you can build any arbitrary demo, get any blind man across Austin in your thing, and you still are just as far away from solving self-driving cars as you were when you started. The demoware is useless.
There's a lot of good insights in the YouTube comments.
What do we got?
They say it's a problem we didn't know we had. That we've invented an entirely new space. And that may be why some people have a hard time understanding how it can be useful. But
Go
ahead.
More? Or I was just going to take a minute to talk about, a bunch of people on Reddit. The subreddit's really full of haters. Think about this as like some like cynical business or marketing move. Like, look at me, right? It's possible that everything about me is a lie. And everything about my identity is constructed in order to do, but does that really make sense? Or think about it a lot more like, we're kind of like an AI research lab. I like to make things that actually ship. I think a lot of people here really like that and like using the things, but it's not like, there's no, and next week we're going to announce our partnership with the city of Beverly Hills to have bodies standing on the corner deterring microaggressions. Right? Like, no. It's just cool, and it's cool to think about. So in terms of like, if you're viewing this from a very utilitarian perspective, like, how will the body improve my life? Don't buy one. And I feel even the same way about the comma stuff. Like, people who are buying it for that purpose and making it very like clear. Oh well, I have to think about how many rational gnats of how many gnats of happiness I will gain by purchasing this. Oh my God, I can't believe people think like this. It's just cool, man.
they want to know more about the arm.
Oh, you want to know more about the arm? All right. So what is the knee? The knee is a 2 degree of freedom thing. We really want to keep the actuators to an absolute minimum. But with the arm, we're going to need 6. right? So you need 6 degrees of freedom because you want your end effector to be placed in any XYZ position and in any roll pitch you want. So what I'd really like to design is like a 4 degree of freedom shoulder that can do, so you can do like the polar interpolation of the shoulder as well as the rotation of the shoulder in like a 3 degree of freedom thing. And then, because you want to keep the motors as close to the thing as possible, right? The less inertia your arm has been moving, the better it is. And then the 4th motor will be here and then belted to the bicep, right? So a 4 degree of freedom assembly here as close to the non-moving part of the arm as possible. And then you have 2 more degrees of freedom to get your 6. You have wrist and forearm rotation. So you can use relatively small motors for that. And then the hand. The hand is even harder than the arm. We were just thinking the first would have a gripper similar to the one on Spot. If you saw the Spot arm. I don't exactly like how the Spot arm does its 6 degrees of freedom because they're not the human ones. The Spot arm does not do, can't do this. It puts this rotation axis over here. It's still 6, but it's not the human 6. I'd like the human 6.
They're making a lot of comments.
What do we got?
If you can pull this off, it'll be huge.
It's a long-term project.
Make driving chill, and it has. The body will make what?
I don't know. I came up with make driving chill like 3 years into Kama. We'll figure out what the body is way less utilitarian than the Open Pilot. Like it's more in the research direction. It's not like don't buy it expecting it to do something. Buy it expecting it to learn things. Buy it if you buy a body and you work on it for a month. I'm gonna give a shout out to Dean Li. Dean Li's a guy in China. He's one of the biggest contributors to OpenPilot and open source. He started out where he started out and where he ended up. The change in his programming ability over those 2 years is unbelievable. So you buy this, you legitimately try to like write features for this, try to improve it, and you'll become. People always asking, how do I become better at programming? Well, it's like, well, how do I get, big arms, right? Well, you gotta lift weights, man. Well, I just want the one magic trick. No, there's no one magic trick. Go to the gym every day, right? So it's like that.
Is this just a meme response to Tesla? Can you just admit that?
Well, we saw Tesla do it, and Tesla this was a revolutionary idea. We'd never ever thought before about building bodies. But when we saw Tesla do it, we were like, we put our top guys on it and we're like, we're gonna copy them. And what we did was we put a broomstick on a hoverboard. No, it's an obvious idea, right? Like, think about it. People are always saying, how are you gonna deal with the fact that the car manufacturers are gonna lock you out? And I mean, like, sure, we could do it with hacking, or we could do it by just building a human, right? And then we can sue people. We gotta get this added to the anti-discrimination laws. Don't discriminate based on brain biochemistry, right? Like just because there's silicon and metal, like, hey man, plur.
They're asking about if the hardware will be open source.
Nope. I'll tell you why not. Open source hardware benefits clone makers and only clone makers. We don't open source hardware because it benefits clone makers. You think, oh, well, okay, there's going to be individuals going out and building this. Not really. It's hardware has so much. It's not like software, right? Like a software is built using a compiler, and the compiler is also open source, and you can download it. And you can have software running in no time. The body has an intricate supply chain, which involves. So you're like, oh, it uses hoverboard parts. Yeah, it uses hoverboard wheels. The motherboard is reworked like crazy. We pull off the knockoff microcontroller on there, and we put a real STM on there. We desolder the resistors, we put another circuit board on there. It's a custom aluminum milled plate. Due to the supply chain complexity, open source hardware does not benefit the individual.
Yeah, I think we should make it clear it's not just a hoverboard we stuck a pole on.
Oh yeah.
There's quite a bit under the hood.
Yeah. Which
For
body
our
would
for our
like to-
late
like,
arrivals who didn't see the
you
picture
ever
inside.
seen a hoverboard that has a solid aluminum plate on the base like that? We can.
Any actuator for neck?
Well, ask why you need it. Right, if you want, so you could think about the 3 degrees of freedom for the camera, yaw, pitch, and roll. Pitch will be handled by the knee. Yaw is handled by the base wheels, and why do you need to roll?
Yeah, I think why aren't more people using shipping first hardware strategy in robotics?
Shipping first hardware strategy because they're run by business losers who are like, well, we have to figure out what the application and the target consumer is for this. Ugh. I think I hate that mentality so much. I think that it's this mentality that you're managing people. Like you view people or customers as like something to be managed and analyzed and, bro, like, I don't know. I think this is pretty cool. To be honest, would I have an OpenPilot thing in my car? Maybe not this rev. Give it a little more time for the software to get more mature. Maybe when 1.0 comes out and it's just easy. Because like my car is something I actually rely on. But would I buy one of these? Yeah, probably.
Why don't we have more robots already, you think?
Because software is really hard. And because with driving, I mean, the common mentality is deliver shippable intermediaries. And there are nice shippable intermediaries in self-driving that don't involve level 5. Right? OpenPilot can already provide a lot of value to people. Building a robot that provides any value at all is quite hard. And we do have robotics. You just don't call it robotics, right? There's a saying in AI, it's something is called AI until it works, then it's just called software, right? Remember when it was like search algorithms? Oh yeah, search algorithms, that's AI. Today, this is not AI, right? And now deep learning is kind of, well, no, I mean, that's not like AI. Like, what's AI, man? Oh, it's like, doing this, fancy, like, it's got to have consciousness or something, right? Like, it's the hard problem that always gets pushed out. So robotics is the same way, right? You have a robot in your home. It washes dishes. It's called a dishwasher. But you don't call it robotics because it works. Robotics is just called all the things that don't work.
What kind of open positions will be for the common body department?
I mean, if there's someone out there who knows a lot about Mujoku, so we're not doing any sort of real classical stuff, but if you know the kind of control theory that's going to let you build good models of these actuators and build a good simulator, we're interested. If someone wants to come work on the simulation environment for the body, I'm interested. And you might not think you have the skills for this, but if you're like a game developer, like that sort of person, someone who's going to build a great, fast, reliable simulation environment for the body, and test it to the real world, not some theoretical academic model, I would hire you. But I think that would be it for the body positions.
Yeah, we can put some comma body parts in the comma part shop, maybe.
Yeah.
Seems reasonable.
I dropped a body 2 days ago and broke this top piece. We'll open source the top piece here. So we'll open source this mount, and you can print other mounts if you'd like to mount other things to your body.
Curious why we used a
Like
hoverboard.
laptop. You put a laptop up here.
What else did we consider?
Nothing. I built the first prototype comma body a year and a half ago now. I went to Best Buy, bought a hoverboard, went to Home Depot, bought a pipe, and stuck it on there. And then they don't balance on their own, so you have to write software to do that. But, what else did we consider? I mean, nothing. Look at this wheel. Look at this wheel. Cheap, available, 250 watts. The only reason these motors are, we say 150 watts is because we're not running them at 36 volts. You can run the motors at 36 volts and get 250. At a board, maybe not, but the motors, you can definitely do that. It just has so much power at such a low price point that they're amazing.
All right, I think that's kind of it from the YouTube.
Cool, yeah, we're almost at 11 o'clock. We got one last question. Anyone here can ask too.
So you referred to sort of the idea of like interacting with things in the real world as kind of like a human-oriented API. If you're controlling a car, as long as you're not locked out, you're basically controlling an API that's been provided for you to control those various things. So it seems very hard to, if you think about, making an omelet or doing laundry or many, many other things, each thing seems like an individual challenge that is quite difficult, even if you have all those degrees of freedom. So ultimately, is there an interim step where a device like a vacuum or a washing machine or something might know that it's being talked to, know that it's being controlled by such a device, and make it easier for such a device to interact with it versus having to do all the human things needed to do extra work?
This is a bad way to think about it. This is the same sort of people who are thinking like, well, wouldn't it be nice if we upgraded our city with smart streets for self-driving cars? Right? This whole mentality, it just involves the reason that cars have APIs to control steering has nothing to do with ADAS features and everything to do with the fact that electrical power steering saves you 1 mile per gallon on the road. Right? They've repurposed something that already exists to provide this small value add feature. They did not put in the adaptive cruise control. It involves a slight change to the braking control, but all the valves are still there. They're the same valves being used for traction control. They're the same valves being used for anti-lock brakes, right? Because these things were repurposed and already in the car, you managed to get these APIs. But I would not try to don't make the world conform to you, conform to the world. Cool. Thanks for all coming out. We got some food. Yeah, this is we're trying. All right? And we're honest. The body is an honest product. It's not a man dancing in a mesh suit. And the man dancing in a mesh suit is still leaps and bounds beyond what does Google promise in robotics? They make some vague emotional claims about how robots and humans are going to coexist. This is show me a real thing or shut up. So I really subscribe to this mentality and we showed you a real thing and it'll get better over time, slowly, iteratively, honestly.
Just one more question.
Yeah.
So not to compare it to a Boston Dynamics robot, but if you were to kick one very hard, would it fall over?
Oh, sure. It's hard, so you can't, with just having the wheels down here, you can't really prevent it. But with this one, I think this one we could get to withstand any human kick. Because you can, shift your weight, especially if you have weight up here, right? If you put, 2 big arms here that weigh 30 pounds, when someone kicks it, okay, I got 30 pounds of weight stabilizing me here. I move my actuators quickly. So no, not that body, but this body with the magic of software. Yeah. Remember also, Boston Dynamics showed one video of it being kicked. They didn't have a carnival day where they invited average people in off the street to kick the robot. Now this is the difference between a demo and reality. I bought the spot and I kicked it and it fell over. Please help. All right, thank you all for watching YouTube. How many people?
We got about 300 people right now.
300 people. Do we want to give them a bagel?
The bagels look amazing.
Oh, you got to go get your own bagel. That's what you get for being remote.